Welcome to Demystifying Math. In this lesson, we're going to be discussing and or probabilities. Probability is the number of favorable outcomes divided by the number of possible outcomes. We're going to find the probability of drawing a king from a deck of cards. We're using a deck of 52 cards, which does not include jokers. The number of favorable outcomes is the number of kings, which is 4. The number of possible outcomes is the number of cards in the deck, which is 52. So your probability is 4 out of 52, or 1/13. Let's find the probability of choosing a heart. There are 13 hearts out of 52 cards, which gives us a probability of 1/4. Now let's find the probability of selecting a king and a heart. Keep in mind that this is just one draw from the deck of cards, so the card has to be both a king and a heart. There is only one card that's a king of hearts, so that's 1 out of 52. When we're looking at the and probability, in this case that's the intersection, so the intersection of kings and hearts. If you want a copy of the diagram of the deck of cards, a link is attached to one of the comments below. Okay, so let's find the probability of drawing a king or a heart. Well, there are 13 hearts and 4 kings. But if I added that together, I would be counting the king of hearts twice. So I need to subtract it out so that I'm not counting the king of hearts twice. So I have the 4 kings, the 13 hearts, and take away one of the king of hearts that I counted twice. So that leaves us with 16 out of 52, or 4/13. In general, you can give a formula for an or probability, where you have the probability of A or B equaling the probability of A plus the probability of B minus the probability of the overlap, or the probability of A and B. When you have a probability of A and B, or an overlap, they are called mutually inclusive events. We have one card that's going to be selected from the bag. We want to find the probability that the card will have a triangle on it. So there are 6 cards in the bag, and 3 have triangles on them. So the probability of a triangle is 3/6, or 1/2. Let's find the probability that it will have an odd number on it. The odd numbers are 1, 3, and 5 in the bag. So that's 5 of them out of 6. So the probability of selecting an odd number would be 5/6. Now let's find the probability that it will have a triangle and an odd number on it. So there are 3 triangles with the numbers 1, 5, and 2 on them. The first 2, 1 and 5, are odd, so that would be 2 out of 6, or 1/3. Again, the intersection of being a triangle and an odd. Let's find the probability of being a triangle or an odd. So we said that we could find the probability of the triangle, which is 3/6, or 1/2, added to the probability of being odd, which is 5/6, and subtract the overlap, where there's 2 that are triangles and odds. Then we'll add that together and we get 6/6, or 1. So if you look at the bag, all the cards either have an odd number on them or a triangle. So you're very certain to get one of those. Let's change our situation a little bit. We're going to draw 2 cards from the bag. So we're going to select one, put it back in the bag, and make our second selection. That's what with replacement means. Let's draw a tree diagram to help us with this. On your first draw, you can pick any of the 6 cards. So one with a circle, or one with a triangle, a 2, a 3, or either of the 2 5s. Then on your second draw, because you put the card back in, you still have all the same cards to choose from. So you still have 6 to choose from. So we have 6 times 6, or 36 possible outcomes. So keep in mind that we're multiplying for this situation. What is the probability that a 3 and then a 5 are selected? Well, we want it in that particular order, so there's 2 ways to get a 3 and then a 5 out of 36. So you have a 1/18th probability. We can find this an easier way by multiplying probabilities. We can multiply the probability of a 3 times the probability of a 5 and get the same solution. So the probability of a 3 on the first draw is 1/6 because there's 1 3 in the bag. Now keep in mind that we're putting the 3 back in the bag, so we still have 6 to choose from for the second draw, and this time we want a 5. And there are 2 5s. So 2/6 would be our probability of getting a 5 on the second draw. So that gives us 2 out of 36, or the 1/18th again. Next time, what we're going to do is find 2 cards that are going to be selected without replacement. This means that if we pick a card on our first draw, we're going to hold it out and then draw again. So on our first draw, in this case, we'll have 6 to draw from, and on our second draw, we're only going to have 5 cards left. So let's look at that tree diagram. We have the same first 6 in our first column. And then here, let's suppose that this was the one with the circle on it. Then this will be the one with the triangle, and the 2 and the 3 and the 2 5s. But I don't want to put the one with the circle here again because I'm going to hold that one out because I drew it on the first draw. If we drew the 2 on the first draw, then we can't draw a 2 on the second draw. But we can draw either the 1s, the 3, or the 2 5s. So this is giving us 6 possibles on our first draw, but 5 on our second draw, which means that we have 30 possible outcomes. Now let's look at this situation again. We want to find the probability that we get a 3 and then a 5. Well, according to our tree diagram, there's still 2 ways to get a 3 and then a 5, but we're taking out a 30 instead of 36. So we have a 1/15th probability. Again, we could have multiplied our 2 probabilities together. So the probability of a 3 on the first draw is 1/6. The probability of 5 on the second, because we are now holding out the 3, we're always holding out what we wanted on the first draw. So we only have 5 cards to choose from, and 2 are 5s. So 2/5 would be our probability of getting a 5 on the second draw. To give us 2/30th, or 1/15th, is our probability. Okay, let's use our formula to help us with a deck of cards. We want to find the probability that the 2 cards drawn are both 4s. So we have 4 4s in the deck. So on our first draw, the probability of the 4 is 4 out of 52. Because we're doing it with replacement, we're putting the 4 back into the deck. And we're going to draw again. So our probability is again 4 out of 52. Which gives us a probability of 1 out of 169 when we multiply them together. Let's do the same thing, except we're going to do it without replacement. So the probability of a 4 on the first draw is still 4 out of 52. On the second draw, we're holding out the 4. We're always going to hold out what we wanted on the first draw. So we're holding a 4 in our hand, and we're going to draw from the bag and try to get another 4. Well, there's only 3 of them to choose from now, and there's only 51 cards because we're holding out one of the cards. So we now have 3 out of 51 as our probability as a 4 on the second draw, which gives us a probability of 4 over 221. This formula is not going to work if your events are dependent and mutually inclusive. For instance, if you were drawing a king and then a red card, They are dependent because we're doing it without replacement, and mutually inclusive because there are kings that are red cards, so there's an intersection. So what happens is we don't know what we're getting on the first draw. So if we draw and we get a king, we don't know if that king is red or black. So we don't know what the probability of the second draw is. So just keep in mind that it will not work for situations that are dependent and mutually inclusive. All right, thank you for watching.